Thanks everyone for attending my presentation. I'll be discussing some different aspects of nanoIR, focusing mainly on different types of sample preparation, some of the data types that come out of the instrument, and then go briefly into some of the applications of this new technique in materials characterization. So I just want to take a step back and do a quick overview of nanoIR just to give everyone a quick introduction and get them up to speed. But to do that, I need to take a step back and go over what is vibrational spectroscopy and its role within materials characterization. So when we speak of vibrational spectroscopy, we're mainly talking about Raman and FTIR, and these tools are often used to identify the structure of different compounds that we find within materials. So what we have is a collection of fingerprints or vibrations that form a spectrum. And that sort of gives us a fingerprint that we can go back to match within a library to identify what that specific compound is. So this is very powerful if you have, say, a contaminant or some material that you just want to find the identification of. You can send it to these types of vibrational spectroscopy. And often it can tell you either the exact compound or the classification of compound that it falls within. But one of the major limitations of these vibrational spectroscopy-based techniques is that they are diffraction limited because we use light as an optical probe. So by diffraction limited, I mean it's limited to relatively low spatial resolution, roughly half the wavelength of the probing light. But in typical applications, what we find is that with Raman, you're looking at around 1 micron resolution, whereas with FTIR, you're looking at tens of microns, roughly 50 to 20 in most cases. So that sort of leads into nanoIR, and what this is essentially we're using an AFM cantilever as a near-field detector for infrared absorbance. And what happens is sort of a four-step process where we first position the cantilever at the region of interest and then irradiate the sample with an IR source at a fixed frequency. And then the sample will have a response if it absorbs the infrared light, and that response is going to induce a force that displaces the cantilever. And because this displaced force is local to the probe tip, we can essentially bypass the optical diffraction limit of these vibrational spectroscopy techniques. So what we're essentially working with is roughly 5 to 30 nanometers of spatial resolution, which is significantly improved relative to FTIR and Raman. But the resolution or the range of analyses that you have access to is often limited to the laser sources that the nanoIR is supplied with. So in our case, we're using 2 pulse tunable infrared lasers, an OPO, which covers the high wave number region, so 4,000 to roughly 2,700 wave numbers. This has your CH, OH, and NH stretches, and then a QCL, which covers roughly 1860 to 751 wave numbers. And these have most of the key fingerprint bands for many organics, and we can pick up some peaks from certain inorganic compounds. But what we don't have access to because of our spectral resolution is this middle region that has some few key functional groups that might be of interest, such as nitriles, silanes, and alkynes. And then also below 750 is where most inorganics are found. So we can't access those. But anything within the range that we have access to can be probed by the nanoIR technique. So in terms of the data that comes out of the nanoIR, there's 2 main types or classes. There's the spectra, which you measure the cantilever response across the entire IR laser range, and these are analogous to FTIR spectra. And we also have chemical maps where we essentially sweep the probe across the sample surface while the laser is held at a fixed wave number. So just to go a bit further in depth into how this sort of process happens for each of these types of data, when we do tip localized spectra, what happens is we fix the position of the probe at a particular region of interest. And then we irradiate the sample and measure if there is a sample response. If there is absorbance, then the sample response induces a probe response. And we essentially measure that and tune the laser to the next frequency and continue across the entire spectral range. So in essence, what you get is you're monitoring the cantilever response as a function of wave number, and that in essence regenerates the nanoIR spectra. But one thing to note is that these are often collected at a single wave number at a time. So unlike FTIR, where you're passing in a packet of frequencies and measuring the loss at each, we're only passing in a single frequency at a time and measuring the cantilever response as a function of that. If we switch over to chemical maps, what we're doing here is just switching the fixed and variable parameters. So we're fixing the frequency of the infrared laser in this case, often tuning it to some frequency of interest, such as a carbonyl bond or a silicon oxide bond, essentially some function group that we want to map out the spatial distribution of within our sample. And again, we follow this similar loop where we irradiate and measure sample and probe response. But what we're doing next is moving the probe to the next position in the image. So essentially what we're getting here is we're collecting the distribution of the compound at a single frequency as a function of position, and these are collected simultaneously with the AFM images. So you can go back and correlate different features such as topography back to the distribution of chemical species. There's a couple of other more advanced types of data that you can get within AFM or nanoIR. One of them is hyperspectra, where essentially you're doing spatially resolved spectra by collecting them in an array. And essentially what you have is a cube of data where each one of those pixels is a full spectrum. So what you can do is go back and select specific pixels and look at the entire spectra at that region or at that feature. Or you can take a single wave number and splice across all of the pixels to reconstruct essentially what is a chemical map. So in essence, what we're getting is spectra at each pixel across all wave numbers, or chemical maps where you have a single wave number at all pixels. But one of the big trade-offs of these types of data is that they are very time consuming to collect. So often collecting a hyperspectral image is at the trade-off of lower quality of the spectra and maps relative to if you just conducted analyses with just spectra or just chemical maps. If you want to study these types of data sets but increase the resolution, what you can do is just reduce the amount of dimensions you're collecting across. So in the most extreme case, you just constrict it to a single line scan across an interface, and then you can increase the density of the points within that region that you're line scanning. So what this essentially gives you is just spectra as a function of one direction, and you can look at how different features change as you cross a interface or boundary. And you can also project them to see multiple peaks grow and change at the same time. But in essence, what you might want to use these types of high density line scans or hyperspectra for is if you're doing multivariate analyses where you need to look at many peaks at the same time. If you're just doing exploratory analyses where you essentially don't know what you're looking for, sometimes it's a good idea to just collect a huge array of data and then find out what the trends are across your sample and then go back and either re-image it or recollect spectra with higher resolution. And the last is if you need to track the distribution of multiple vibrations at the same time. Sometimes if you're tracking, say, like 10 or 20 peaks at once, it makes more sense to do a hyperspectra rather than collect 10 or 20 chemical maps. So using these types of data, you can really address three main questions or properties within your sample. The first is because it's tied to an AFM, you can image the sample and determine what the sample looks like. And you can map out the sample to see how different compounds are distributed spatially. And then the spectra can be used similar to vibrational spectroscopy analyses to determine what your sample is really made of. So this is just a quick example. We have just some random materials that were found on top of a surface. And what we see is there's a couple of different types of materials. There's this film-like residue spanning across the entire image, and some particles with different morphologies, some tall and small, and some relatively flat and large. And what we can do is specify precise probe positions on each of these features to collect the spectra from. And so this is the sort of data that we would be working with. So we can park the probe at each of these different features that are color coordinated to their corresponding spectra. And what we can see is that this small round particle, we see some carboxylate features. And then the tall particle that sort of agglomerates to it, we don't see any peaks, suggesting that it's an IR active compound like some inorganic. On the film-like residue, we can see that in the taller parts, we see this sort of carbonyl bond, C double bond O, likely some type of ester or acrylate. And when we look at a smaller, thinner region, say in black, we see evidence of the substrate. And that is this red one here, which we see a lot of SiO-Si stretches, indicative of either glass or some silicon oxide. And if we take just this carbonyl bond at around 1730, what we can see is that if we map it out, it's mostly concentrated within this film-like structure. All of the other features show basically no absorbance. So again, we're looking at three things: the composition with spectra, the appearance with the chemical, or the appearance with the AFM images, and then the distribution with the chemical maps. But you're not just confined to looking at nanoscale or submicron materials. Sometimes you have these contaminants or features that are just a little too small to access with FTIR. Essentially, with these materials, we can just park the probe on top of it and take spectra, and we don't need to image it at all to really precisely position the probe because it's so large relative to the analysis spot size. So in this case, we have some contaminant on a wafer surface that's roughly 10 by 20 microns, so a bit too small for FTIR, but we can readily just analyze this with nanoIR and find out it's some type of phenolic dye by comparing it back to our libraries. And we also have access, similar to FTIR, to look at mixtures or multi-component materials. So in this case, we had a PMMA polystyrene film that was cast onto a wafer. And what we find is that the spectral features are predominantly PMMA and polystyrene. That is those references in orange and blue. But we also see some trace peaks that are due to hydrocarbons and silicone or PDMS, shown in green and red. So now that we have sort of an idea of how the different types of data and questions that can be answered with nanoIR, what I want to go briefly into is sample preparation, because this is a huge part of getting your material compatible and ready for analysis in this tool. So in terms of just macroscopic restrictions, there's a lot of similar restrictions as in AFM. That is, the physical size can't be too large to fit in the scanner stage. It can't be too rough, otherwise we can't accommodate that with the range of motion that the AFM scanner head has. And also if the sample is too curved, then similar to the roughness, we just can't accommodate the changes in height across the entire region. There's also a couple of other restrictions because we have additional mirrors for the infrared lasers. So you don't want to have features of your sample such as raised pieces, or if it's really curved, then you don't want parts of your sample to bump into the additional optics or block the beam path of the infrared source. And I wish that there was like a one size fits all sort of recipe, but the sample prep is very dependent on the types of questions you want to have answered, in addition to the material that you have. So the general rule of thumb for this technique is the flatter and smoother you can get your sample, the better the quality of the data and resolution will be. If your sample is too large to fit inside of the chamber, or it bumps with some of the optics or hardware within it, then you just have to cut and cleave it so that it fits according to shape. If you have something like a loose particle, say like aerosols or bacteria or anything like that sort, you have to adhere them relatively well to the substrate so they don't move while you're imaging and analyzing them. And this could be done through impactors or solvent adsorption, or numerous other types of methods. And then lastly, if you want to expose the z-axis or cross-section to sample, then you have to cut it. And that, of course, depends on the type of material you have. If you have all hard materials, you can typically just cut or cleave it and polish it down to the smoothness that is needed. If you have softer materials, then microtoning or car microtoning is typically a good solution. And if you have a mixture, then this is a lot more challenging, and you would have to have a more in-depth discussion or look into see how your different materials respond to different cutting methods. But I just wanted to go into some cases of where we've tried different sample preps and how they affect the overall data that we get. So in terms of looking at the spectra, this is a polystyrene sample that was milled with an ion beam. And what we find is that there is some degradation or damage to the polymer by these additional peaks that appear relative to the reference compound. And if you try to, say, clean that sample using plasma, then instead of just cleaning off these additional degradation products, what we end up forming is oxidized species. So you have to be careful with your cutting and cleaning methods that you're not chemically changing the surface of interest. Additionally, if you're cutting a sample, you want to make sure that you're also not physically changing it if you're trying to accurately measure, say, how thick a specific layer in your material is. So in this case, this was a cross-section of a 3-part polymer interface. And what we find is that there is a lot of spreading or bleeding between the different compounds. As you can see from these 2 chemical maps. At the interface, it's sort of blurry between both of the chemical maps, suggesting that the materials were spread as this cross-section was prepped. And last but not least is if the sample has been, say, in an SEM and has been coated previously in some reflective metal, such as iridium, gold, or platinum, these metals are highly reflective across the infrared region, which means that if we shine an infrared source on it, most of the light will be reflected or scattered off the surface, and we won't really be measuring much absorbance. So in this case, we're looking at a thick acrylic resin slab with and without a platinum iridium coating on it. And what we can see is that when we look at the coated sample, we lose access to resolve all of the key peaks of the acrylic resin. That is the 1730 peak from the ester groups. It's completely unresolvable in the coated sample. So depending on the type of question that you have, you can orient your sample differently. If you're looking at the distribution of species across your surface, then you can just look at it in a top-down view to look at either the coverage, say, of a coating or the distribution of certain compounds. But if you're looking for differences as a function of depth or Z, then often it's better to cross-section the sample to expose that Z-axis so that we can look at the layer or depth composition as well as different thicknesses of different materials within the sample. So just to go over a couple of quick examples, what I'll go into first is a polystyrene PMMA mixture that was cast onto a silicon substrate. And because this is a mixture that we knew in advance, we have either spectra information a priori, we can take those prior information to guide the analysis. So in this case, we know we need a map up for polystyrene at 1494 wave number and PMMA at 1730 wave number. And what we can see is that the PMMA is not homogeneously distributed within the polystyrene rich region, suggesting some phase separation. So we can look at the distribution of multiple compounds to see how the distribution of them matches up with one another or differs in this case. This is another example where we have an unknown particle on a silicon substrate. And in this case, because we don't know what the compound is, we want to take spectra initially to figure out if there are any differences within this single particle. So if we take spectra at the center and edge, what we find is that the features are actually fairly different. We see hydrocarbon bends in both spectra, but the edge of the particle, we see this broad intense peak around 1600 wave number, which is due to hydroxyl groups, likely water in this particle. And if we then go back and take these peaks and map it out, what we find is that the whole particle, we see these CH groups as indicated by the 1450 wave number map, but the water is most concentrated in the very edge of this particle. So we can look at the distribution of specific function groups even within single particles to sort of figure out, is it homogeneous, is it phase separated? Questions like these can be readily answered with nanoIR. And there's other applications for this, probably many more than can be listed or that I'll go over, but some other ones include nanostructures or fabricated patterns. If you have deposited particles, I showed one example of that. If you have surface residues or contaminants, this is also a great technique, especially if you can't readily access them with, say, Raman or FTIR. And then lastly, if you have some type of coating, typically if it's thick enough or smooth enough, we can map out, how homogeneous or well distributed that coating is. So pivoting over briefly to looking at cross sections, in this case, we're again looking at the composition throughout the sample, so as a function of the depth or Z component. So this is a microtomed multi-layered polymer film, and what we're looking at or what we're interested in is this middle interface layer that's in this red box. And just for reference, if we were to analyze this with FTIR, this blue box shows sort of the analytical spot size that we're working with. And when we take spectra from this region, if you examine the spectra shown in black, what we see is that we don't pick up really any features of the polymer, but rather we're picking up the embedding resin material instead. But with nanoIR, what we can do is go into that specific region of interest, take spectra across each of those 3 different layers, find that they are chemically distinct, and also map out the distribution of them. So in this case, we see that layers 1 and 3 have similar features, but layer 2 is completely different. And those are also well reflected within the chemical map. So there's a couple of other applications that you can go into with cross-section materials if you have contaminants that are buried within your sample. Often you can cut the sample and expose that contaminant for more ready access with nanoIR. You can also look at layered materials and films as I just showed, or if you have something like a sidewall, if you cleave the sample, you can in essence expose that sidewall, and we can readily access that with nanoIR. So in terms of how this sort of matches up with other techniques, if we speak just towards the imaging side, what we can see is that it really gives you the molecular level information that you need to identify what compound you might be dealing with. So an example is if you're doing, say, EDS or EELS on a sample and you see that it is carbon and oxygen rich, that doesn't really tell you much more aside from the fact that you might have some type of polymeric material on your sample. But what nanoIR can do, because it's tied back to vibrational spectroscopy, is tell you that you have, say, an ester or a cellulose type of material. So it really sort of helps you narrow down specific compounds that could be on your sample. So again, just taking a step back, there's 3 categories or questions you can address with nanoIR. That is what the sample looks like, how its different compounds are distributed, and then lastly, what is your sample made of. So if any of these questions are of interest and you need to access spatial resolutions that you can't access with other vibrational spectroscopy techniques, then nanoIR might be a good avenue for analyzing your sample with. So lastly, this is what the instrument looks like. And with that, I will take any questions.